All right, let's start Unit 3, Transformations in the Plane. We'll begin by talking about congruence transformations. You should be able to figure out what that means. Congruence, we've talked about, means same shape, same size. And we'll talk about what transformations are, which, if you've ever worked with transformers or watched the movie, you probably know what a transformation is. So let's begin working. Okay, what is a congruence transformation? Taking a look at the picture here, can you define what is a rigid transformation? This is an example of a rigid transformation here. This shape becomes this one. That doesn't help. Let's take a look at this example. This is a non-rigid transformation. To go from this original shape to the new shape. Can you figure out what the definition of a rigid transformation is? So here we go, a rigid transformation. So if we're taking this shape to the new shape, original to new, these are non-rigid. Okay, so by definition, a rigid transformation is one that preserves the size and shape of a figure. Kind of like our definition of congruence. So rigid transformation is kind of the same thing as congruence transformation. So the example on top, what kind of transformation is that where you're taking the house and moving it somewhere else? Well, it maintains the same shape and size, it just goes somewhere else. That would be a rigid transformation. Transformers, they go from a semi to a monster, or a car to a monster. That would be a non-rigid transformation. Sorry, I called them a monster. I don't know if they're really a monster. I don't watch the movies, so anyway. Some more definitions for you. Transformations in the plane move or change a figure to produce a new figure. A rigid transformation is a transformation preserving length, angle, measure, and area. Rigid motion is also known as an isometry. So those are all similar terms that we come across. Isometry, rigid motion, congruence transformation. So let's take a look at some of the types of rigid motions. We have a translation, a reflection, and a rotation. Notice figures are congruent if and only if the corresponding sides and angles are congruent. So we can move the figure, it still maintains the same shape and size. We can flip it across a line, same thing. We can rotate it around a point, same thing. So let's take a look at the rigid motions that we use to perform this congruence. To move the blue figure onto the red figure. So to go from blue to red, that is a rotation around point P. And to be more descriptive, we could say a clockwise rotation, since it's moving in the direction of a clock. B, well, first we go to the green, so that would be a translation. And then we flip it across the line, that would be a reflection. And that would be a double, a composition of transformations. We'll get more into those later on in our unit. Right now we're just looking at the basic transformations. Okay, so remember when we do a transformation, a rigid motion, they need to maintain the same shape and size. So if we're going from figure A to figure B, they should maintain the same shape and size. So we could take a look at this figure and see if it does indeed do that. So I would translate it over, and then I could rotate it. Oops. Didn't want to do that. Keep the same size. Rotate it around. Translate it down. Notice it does not maintain the same shape. So it would not be a rigid transformation. We see this transformations everywhere. Makes nice, neat patterns. One way is in quilts. So take a look as how do we get from figure A to figure B? Kind of a transformation is that? It just looks like it's moving the figure over, so that would be a translation. Whoops, can't spell. So we're translating it to the right. And then if we're going from figure C to figure D, notice the congruent figures. We have these segments that are marked as congruent. Those are congruent, and these angles are congruent, and these both have a 90-degree angle. So in order to get from C to D, we have to rotate that figure. So it would be a rotation. And I could rotate it clockwise or counterclockwise. It doesn't matter around this point. Or you could call it rotation and then translate it over. Okay. So some more information on transformations and how we write them. As we talk about them, a transformation moves or changes the geometric figure. The new figure is called the image. And the way that we write that in geometry is you have the original figure first, then an arrow, and then the image. The order of the letters is important. The A in triangle ABC matches up with the P in triangle PQR, which means those angles are congruent. Angle B and angle Q are congruent. Angle C and angle R are congruent. Same way that segment AB is the same length as segment PQ. Okay. So as we talked about, translation moves in the direction and the same distance. Every point and in the figure moves the same distance and same direction in order to keep same shape and size. Reflection uses a line similar to a mirror. Rotations have a fixed point that it goes around, which is known as the center of rotation. So as you can see in the next slide here are some more examples. We're reflecting across a horizontal line, rotating around a point, translating in a straight path. So now let's take a look at how we write this using the coordinate plane. Okay, so I've taken a figure, a triangle, listed its coordinates, and put them on the coordinate plane. So let's apply the first transformation. Remember, the first column before the arrow, we refer to that as the original. It's also known as the pre-image. And after the arrow, the new one is known as the image. That arrow just indicates a transformation occurred. Now in the first example, it says we have the coordinates x and y. And it says the new x coordinate becomes x minus 7. So I take the x coordinate, the original, and subtract 7. So my new one, my image now, I will adjust. And the y coordinate, we're adding 1. So my image will be negative 7, 1. Negative 5, 1. And negative 7, 3. And I can graph that on my graph. Negative 7, 1. Negative 5, 1. And negative 7, 3. Notice, what is that? Looks like a translation. Okay, maintains same shape and size. Take a look at the next example in red. Notice in this transformation, the x stays the same, but the y becomes opposite of y. So I'm looking at my original. So keep in mind, this all comes from the original figure. This particular transformation, we get 0, 0, because the opposite of 0 is 0. 2, 0. And 0, 2 becomes 0, negative 2. Graph those. And what does it look like? It looks like it flips over the x-axis. That would be a reflection across the x-axis. Next example, xy becomes opposite of xy. So if I look at my original coordinates, I'll put my new image in blue. So 0, 0 becomes 0, 0. 2, 0 becomes negative 2, 0, because that x became the opposite. final coordinate stays at 0, 2. Graph that. 0, 0, negative 2, 0, and 0, 2. What happens? That thing flipped across the y-axis. And finally, in green, that rule says we take opposite of x, opposite of y. So I'll get 0, 0, 2, 0 becomes negative 2, 0, 0, 2 becomes 0, negative 2. Graph that one. And looks like that one rotates around. Rotates about the origin. So that's we could say it's a 180-degree rotation around the origin. Remember, the origin is 0, 0. Okay? So those are some examples where we're using the coordinate plane. How would you reflect a figure in the x-axis if we're given half of it? Reflecting across the x means each point needs to be the same distance away from the x-axis on the opposite side. So this point here is 2 above the line, so we'll go 2 below. This point here, same thing, go directly above, directly below. This point is 4 units up, so we'll go 4 units below. We can then connect the dots, and there we go. An arrow pointing us forward. Next slide. Okay, so let's talk about a little bit more about rotations. Okay, I talked about clockwise, counterclockwise before. Just the way the clock turns, clockwise, counterclockwise. The angle of rotation is the angle formed as we connect one point to its center of rotation and connect that same point. What is the angle formed? So this is a 90-degree angle. This is a 60-degree angle. We know that distances from the center from each point will be the same. So if I were to connect this point here, it would form a 90-degree angle. Same with this one. Same with this one. Those are all 90-degree angles. So we could do the same thing and test the points to see if it is a rotation on the coordinate plane. So I'll graph those on there. You can pause and graph those and see if you believe those are rotations or not. So as we take a look at this first example, mark this one in green. AB is supposed to rotate over to CD. It's marked in red. So you can see that the length of AB over 2, up 2. CD is the length of down 2 over 2, so it's the same length. We can see that as it rotates, A matches up with B. Looks like it's a 90-degree angle. C matches up with D in a 90-degree angle as well. Okay? So it maintains that same angle of rotation. So we would say yes, that is a rotation, 90 degrees clockwise. And the second example has started in blue. It's supposed to rotate onto CD. Notice it's a length over 1 up 2. This one is up 1 over 2, so they have the same length. Let's look at their rotation. So A is supposed to match up to C. And it's supposed to have the same angle as B to D. Notice that that's a bigger angle, so it would not be a rotation around the origin. All right, so that does it. That'll wrap up our talk on congruence transformations. We've identified what is a rigid transformation, maintains size and shape. We've talked about the 3 types: translation, reflection, rotation. We've identified what they look like and looked at different examples, how we write them, making sure to match up corresponding angles and side lengths. We've also taken a look at how it works on a coordinate plane and using coordinate notation. So you've got some practice problems. Put all your knowledge into work. We'll see you next time.